In these videos, we're going to take a closer look at Kubernetes pods. A pod in Kubernetes is the smallest deployable unit of compute and is quite simply a group of one or more containers. Containers will share the networking provided by the pod, and they will communicate within the pod using localhost. Each pod is assigned its own unique IP address within the Kubernetes cluster. Containers in a pod can communicate with each other via inter-process communication, IPC. So this is great for running entire applications within a pod. And therefore, a pod can encapsulate an application, its dependencies, shared storage, and networking into a single deployable unit. Let's get hands-on and take a look at this in action. We're going to make use of the Nginx web server to run a simple Kubernetes pod with a single Nginx container. For this, we're going to execute kubectl with a parameter of run. Nginx will be the name of our pod, and we're going to make use of the official Nginx container image. And with this done, this will now be running as a pod. And we can see this by executing a kubectl get pods. Although this is running, we haven't got much information on the pod or any visibility into the startup of that pod. We can, however, make use of the kubectl logs parameter to see the logs for the particular pod. So we'll use kubectl again. The parameter is logs, and we're querying a pod with the name Nginx. Something to note here, I like to use name/component as a standard, but in the case of pods and pods being the default entity in Kubernetes, for this example, you could just run a kubectl logs Nginx. Let's run the get pods command again, but this time we're going to add on the -o wide option. We can see more information such as the IP address for the pod and the node in which it is running. Depending on how and where you are running Kubernetes, you may or may not be able to access the pod IP address. It will depend on different factors, how you are running Kubernetes and where you are in relation to the kubectl command. So, for example, were you running kubectl directly on the Kubernetes infrastructure or somewhere else like your desktop? In this example, I'm running kubectl directly on the Kubernetes infrastructure. Therefore, the system I am on is part of the Kubernetes cluster, and because of this, I am able to ping the pod IP address. The pod IP address would be accessible from any node in the cluster. For example, we could use SSH to hop onto another node in the cluster and then run ping from that node. And as you can see, that's working as expected. And the same would apply from our other node. In our lab, there is a convenient reverse proxy that will allow you to connect to any web service running in our Kubernetes cluster from the viewpoint of a particular Kubernetes instance. So here we can see our Nginx pod working from the control plane and from worker 1 and from worker 2. However, you won't always be in a lab environment. Sometimes you'll be working on your Kubernetes instance, which is running on your own system. It could be a remote Kubernetes system running in the cloud. Regardless of where the Kubernetes cluster is, you will be working with the kubectl command line tool. Kubectl has a fantastic port forwarding option for accessing network services in a Kubernetes cluster. I'm going to show you this in the lab environment, but technically you could use this approach with any Kubernetes environment to access network services locally on your system. The help examples are really useful. So if you run a kubectl port --forward --help, we're going to port forward our Nginx pod so that it is listening on port 8080 on the system that we're actually running kubectl. As I say, I'm using a lab here, but this could just as easily be your desktop. This will then create a port forwarding tunnel to port 80 of the pod in the Kubernetes cluster. And we can see that it is listening on our local host as the IP it's using is 127.0.0.1. And if you were running this on your own local machine, you would be able to browse to localhost 8080 or 127.0.0.1 8080, and you would see the Nginx welcome page. As we're in the lab, I'm going to show this from a lab viewpoint. So I'm choosing the control plane instance. The target for this will be 127.0.0.1. We enter a port of 8080 and we press go. And that's working as expected. So do remember this and use this approach as you work with Kubernetes clusters wherever they are. For now, I'm just going to Control-C that tunnel and close that down. An alternative way in which we could query our running pod is from another pod that actually has curl. Curl, to recap, is a CLI-based command for interacting with websites from the command line, and there's a convenient curl image that we can make use of. Let's spin up another pod using this image. We'll use it to query our Nginx pod IP address and to return the output as text. So we'll do a kubectl run -it for interactive -rm to clean up. Curl is the name of the pod. We'll use the image of curl images /curl. We'll put --restart as never. So this means if it fails, don't try to restart. -- as the parameter separator. The default command for the curl images curl image is curl. So we want to pass a parameter to the curl command, and the parameter will be the IP address that we wish to curl. In our case, the IP address of our Nginx pod. And with that, we can actually see the Nginx welcome page HTML. The main takeaway on this is that we have two independent pods communicating with each other. And these could have been on any node in our Kubernetes cluster, yet they would be able to communicate with each other using the pod's IP address without any complicated network setup or requirements such as NAT, Network Address Translation. We can also see that the curl pod has cleaned up after itself after we exited because we used --rm. Therefore, we can now only see one pod running. Let's try something different. Let's run a Ubuntu pod and we'll let this run in the background. We'll specify the image as Ubuntu. We'll name the pod Ubuntu. The command we're going to run is sleep, and we'll pass the parameter of infinity, i.e. sleep for infinity. And we can now see this is running in our get pods output. And now, using kubectl, we can, if we desire, execute additional processes in a running pod. For this example, let's run the bash shell inside the Ubuntu pod, which at the moment is just running sleep infinity. We'll do a kubectl exec -it for interactive. Ubuntu is the name of our pod, -- and then the command of bash, so that we run a bash shell in this pod. Now, we're in the container inside that pod. Notice how the command prompt color and the host name has changed. If we do a ps-ef, you can now see that we have PID1, the process that was started for this pod, which in our case is sleep with the parameter infinity. When we did the kubectl exec, it spawned a process for the bash shell, which we are now in. When we ran ps-ef, it also captured this in the output, and you can see that our bash shell is the parent process. As this is Ubuntu running in a container in a pod, we could, for example, interact with this as a standard Ubuntu instance. We'll update apt, the advanced package tool, and then we'll use apt to install curl. And with that done, we can actually use curl to query Nginx via the pod IP address. So that's an alternative approach of accessing a pod from another pod. Let's exit that and we'll clean up our pods. So we'll do a kubectl delete pod/nginx pod/Ubuntu, and in older versions of Kubernetes, we would have used the --grace -period equals 0 to remove entities without any delay. On newer versions of Kubernetes, you can just use --now, which is easier to type and easier to remember. So far, all of the pods we've been running have been via the command line and have been a single container pod. But it's also possible to create pods using a YAML declaration. We're going to explore the use of YAML and creating pods with multiple containers. If you're not familiar with YAML, it is a simple data serialization language that is often used when defining configuration files. The great thing is we can often use kubectl to assist us with fast-tracking the YAML content that we need. If you recall, when we ran the Nginx pod earlier, we executed kubectl run nginx --image equals nginx. Let's modify this and we're going to add --dry-run equals client. We're also going to add -oyaml to output to YAML. And we're going to pipe this to T with a file name. This will act as a T-junction and will output to the screen and will save the output to a file. We have our YAML declaration for the pod, and in this we can see lots of information. I bring your attention to the restart policy. This has a default value of always, meaning it will always attempt to restart this pod if it fails. Valid options here are always, never, and on failure. If you ever want to know more about a particular section of the specification, you can use the kubectl explain option to show this. So, for example, to get more information for the restart policy options, we can run kubectl explain pod. So that's referenced as _, then .spec and .restart policy. And there we can see the possible values and where to go for more information. With our YAML file, we can now use either kubectl create or kubectl apply to action this. Create is considered an imperative command. The commands create, replace, or delete are all classed as imperative. If, for example, you created this item and then you tried to create it again, you'd get an error as you can only create something once. Kubectl apply, on the other hand, is a declarative approach. We are declaring that we would like this entity to look like this. If you're expecting to change the YAML at any point in the future, then it's best to start with kubectl apply. You can technically use create, but you'll get a warning when you then try to use apply on that resource. In the majority of cases, people use apply most of the time rather than using create. Both options will work if the object doesn't exist, but I like you having full awareness of the different options. So let's try this out. We'll use create on the first attempt. So that succeeded, and if we try a create again, that fails. And from here, we could run an apply. We'll get a warning the first time, but going forward, we could continue to apply this without any warnings. Let's get the YAML declaration for Ubuntu pod. We're going to send this to the screen and also to a file called ubuntu.yaml. So let's run an apply on this and take a look at our pods. Again, we have both of our pods running, but this time we've run these via YAML files. So let's just remove these for now. Currently we have two separate files, but a YAML file can contain multiple declarations. Let's combine these two files and take a look. So we're going to make use of curly brackets to group these commands. So let's cat the first file of nginx, a semicolon for the next command. We'll echo --, which in YAML is a separator between entries, and a semicolon to finish that. We'll then cat the Ubuntu file, another semicolon, and we'll close off these brackets. Finally, we'll tee this to a file called combined.yaml. Now, if we apply this single file, it will create both entities at the same time. And we can also delete both of these by using delete and specifying the file with -f. Again, we're going to add the --now option to speed this up. In these examples so far, we've had two pods, each running a single container. Let's change this so it is one pod running two containers. We'll make this a single pod with a web server and a simple example of what is known as a sidecar, where you have a container on the side as a sidecar, like you'd see on a motorbike. Sidecars are typically used to carry out a specific task within a pod. So let's edit our combined YAML file. And we can see there, the containers in each section are a list. In YAML, a dash indicates a list, i.e. a list of containers, and it is one item in the list for the nginx and Ubuntu example. We're going to take the entry from below and add it to the top, and we'll just get rid of that bottom section. At the moment, this is a little bit messy as the order is different in our first container to the second. It's still valid YAML, but this list starts with an image and this one starts with args. Let's just give these a tweak to make them more readable. Personally, I like to have the name of the container as the first entry, then the image. So I'm going to do this for both of these. You don't actually need to do this, but in the long run, readability is always great, especially when you're collaborating with others. So that's looking good, and let's just tweak the metadata labels and the names of our containers. So we're going to call our pod mypod for simplicity. So we're updating both of those that we actually see there. And we'll refer to nginx as the web server, and we'll call our Ubuntu one sidecar. Let's actually make this sidecar do something that we'll actually be able to see. So we're going to use some shell commands. So we'll pass -c for shell parameters as an argument. Then we're going to use a while true loop. We'll have it echoing hello from the sidecar every 5 seconds unless a file called /tmp/crash exists. And if this file exists, we're going to simulate a crash. We're putting this in so that we can actually demonstrate later on what will happen when a container within a pod crashes. So let's save that file. We'll apply it. And now, if we run a get pods, notice that the ready shows 2 of 2 as this is a single pod with 2 containers running in the pod. There's one IP address which is shared amongst the containers in that pod. If we use kubectl describe to show us information about the pod, we can see the IP address and we can see our 2 containers. If we wish, we can curl that IP address, so we'll just use the approach we used previously, but we're going to change the IP address to our new mypod IP. And there we are, that's great. And we can also check that the sidecar is doing what it should be doing by checking the logs for a specific container in the pod. So to do this, we do a kubectl logs, but we also have to specify the container name with the -c option, i.e. inside this pod, which is running multiple containers, show the logs for this particular container. And there we can see the timestamps. What we're going to do now is crash the Sidecar container by creating the file /tmp/crash in the Sidecar container. So for this, we're going to use a kubectl exec to run a command. We use -c again for the specific container, -- for a command, and then we're passing in touch/tmp/crash to create that file which will crash the running container. And now, if we check our pods, you can actually see there that this has errored. And if we check again, it's restarted and the restart count has increased. We can also now see new logs appearing in the Sidecar container. But what if we were interested in the logs prior to it failing? We can actually use the -p option to see these previous logs and note the differences in the timestamps. So with that done, let's now clean up the pod and both of its containers. And while we're here, we'll also clean up those YAML files. So this is our introduction to Kubernetes pods, and rather than just a simple example, we've explored in various ways how to create pods from the CLI, how to create with YAML, declarative versus imperative, and how to run pods with multiple containers. I hope you enjoyed this, and I'll see you in the next lesson.